Welcome, everyone. This is the second, and then we'll have the third lecture as part of the Kavli summer program. So Matt Browning, he did his PhD at the University of Colorado with Yuri Tumre. He had postdoc positions at UC Berkeley and jointly at University of Chicago, and he was at the Canadian Institute for Theoretical Astrophysics after that. In 2013, he was awarded the ERC starting grant for convective heat transport and stellar magnetism. And now he's an associate professor at the University of Exeter. And today he's going to talk about rotation, convection, and magnetism, part 2. So take it away, Matt.
Thanks, Aaron. And thanks again for the invitation to speak. And thanks to many of you for showing up yesterday. It was great to meet some new faces, and thanks for the great questions yesterday. Right, so this is the second in a series of 3 lectures on rotation and convection and magnetism as a kind of subset of this Kavli summer program in astrophysics on fluid dynamics of the sun and other stars. And just to remind you where we got to yesterday, yesterday I gave you a kind of whirlwind observational overview of some of the interesting puzzles that are out there, the observational landscape of stellar rotation and convection and magnetism. And that lecture was pretty squarely aimed at somebody who's coming from maybe a fluid mechanics or plasma physics background, geophysics, but hasn't really worked a lot on stellar astronomy or stellar rotation and magnetism in particular. And the basic punchlines there were just that, look, to 0th order, the structure of a star is pretty insensitive to things like rotation and magnetism. But we can do a lot better than 0th order now. So we have these remarkable observational tools that give us more and more precision on these different axes, okay, of precision in wavelength, precision in time, precision of position on the sky. And as we get better and better at those things, we can learn more and more things. And in particular, we can learn directly about these processes, rotation, magnetism, and convection. There's tons of interesting problems. We can also begin to see how those things affect stellar structure and evolution, which, again, they don't do at the 0th order level, but they do maybe at the sort of 5% level. And that sort of motivates, as astronomers, I mean, these problems are always interesting from the fluids point of view, but from an astronomical point of view, they become interesting once you have the data to actually constrain them. So we're seeking quantitative models of how convection and magnetism and rotation interact in spherical things like a star. Today is a little different. So today the audience I had in mind is just the other side of that coin. Somebody who maybe is familiar with stellar astronomy but doesn't have a ton of experience or as much experience with fluid mechanics or with MHD in particular. So to be really specific about it, the audience that I had in mind as I wrote this was me after I'd taken one fluids class. So, you've seen the Navier-Stokes equations, I'm kind of assuming that everybody who's signed up for a summer school and has gotten into a summer school on fluid dynamics has done that. But you might not have taken an MHD class yet. You might not have taken a fluids class that was sort of applied to stars or planets. And there's some peculiarities to those environments that I think are useful to talk about. So today I want to talk a little bit, sort of 2 parts of the lecture. One is what I would call limiting regimes in rotating fluids. So I want to talk about these asymptotic states that you can find yourself in, balanced states that you can find yourself in, particularly when rotation is rapid or when conductivity is very high. And I want to talk a little bit about magnetohydrodynamics, or MHD, and just to give you a little bit of an intuitive feel for some of the results from that subject. Now, obviously, I'm not going to, this is a 45, 50-minute lecture. I'm not going to teach you these things in that time. Today is more about giving you kind of a scaffolding, an intuitive framework that you can maybe keep in the back of your head if you don't know this stuff already super well. And some of you, there's people here who know this very, very well. But if you haven't learned this stuff already, maybe this is just about giving you a bit of an intuitive framework to keep in mind as you go forward and learn the subject better and better. So I'll do, again, some hydrodynamic stuff in rotating fluid dynamics, so geophysical fluid dynamics, really, and then a bit of MHD. And as time permits, we'll apply some of those things to random problems, basically magnetospheres, accretion, maybe stellar interiors. We'll see what we get to. And the motivation the reason I chose this as one of the 3 lectures is just look, I would say the basic story of fluid mechanics is that the equations, it's very, very difficult to find analytical solutions to them, except in very, very special cases. And that was something that, I mean, maybe after you've taken, again, because the target was me after one silly fluids class. It wasn't a silly class, but I was silly. And the impression that you get maybe after that one class is that you can solve these things analytically. And in most cases, you can't. But you can get insight into the behavior that you're going to find in these much more complicated states where lots of things are competing and the problem is analytically intractable. You can still get intuition for what's going to happen by thinking carefully about which processes dominate over others. And in particular, in cases where just 1 or 2 things are really dominating the behavior, you can find useful constraints on the way the fluid's likely to behave. And sometimes those tendencies persist well into this nonlinear regime that is very, very intractable, sometimes even intractable in simulations. As a kind of specific motivating problem, I want us to think a little bit about just, if you look at a map of pressure contours, so this figure here is just winds on Earth, the little wind vane kind of symbols, and the lines are lines of constant pressure. So you see these high pressure and low pressure regions. And you might expect, before you'd taken any kind of fluid mechanics class at all, you might have expected that you'd have a flow from regions of high pressure to low pressure. But that's not what you see. You see that the wind is mostly along these constant pressure lines. So we'll talk a little bit about why that is and what implications it has for stellar interiors as well. So that's the basic plan. Right. So when I teach this stuff to undergrads, I usually start by saying, look, the good news is there's only a couple of equations. So the only equations I'm going to talk about today are the ones on this slide. So the top one here, the bad news is it's these equations, which some people in the audience, including me, have spent an inordinate fraction of our careers talking about these equations. Anyway, they're complex. There's some complexity hidden in these things, but conceptually they are not hard to understand. Again, I'm going to assume that most of you have seen the top one. This is a version of the momentum equation written in a particular way. So this is just expressing momentum conservation in a fluid. On the left-hand side, we've got acceleration, fluid parcel at a particular spot in space. We've got, on the right-hand side, we can add forces acting on that parcel. So this is just the equivalent of F equals ma for a fluid. So in this particular case, we've got pressure gradients, maybe gravity, we've got a Coriolis term. If we're in a non-rotating, if we're in a rotating, that is a non-inertial frame. And then I've added in terms coming from the Lorentz force associated with the presence of a magnetic field, and a viscous term in a particularly simple way that's appropriate for example, incompressible fluids. So that, different, much fancier versions of this equation. This is the one that we'll talk about today. The equation down at the very bottom of the page is just the continuity equation expressing mass conservation for the fluid. And in the even simpler case, most of the stuff we'll talk about today is the even simpler case where we'll assume the density is constant, the fluid's incompressible, and so this will just become del dot U equals 0. But in general, it looks like this. And then the one in the middle is what's called the induction equation. So this is the subset of MHD that we'll talk about today. MHD, if you really have never seen it before, is essentially just the combination of the equations of fluid dynamics plus Maxwell's equations. I am not going to attempt to spell out all the regimes in which MHD is valid, or the regions in which it's invalid. I'll just say that to a very good approximation, the interiors of stars are well described by the equations of MHD. That is, they're well described by equations in which there is a single fluid component that is magnetized, and the field lines move around. Field lines of magnetic field, let's say, move around in that fluid in a particular way. That's well described by this equation. And we'll talk a bit more about what the equation means and how to interpret it and what the consequences of it are in just a minute. But again, so this equation, the momentum equation at the top here is the basis for essentially all the problems that we'll talk about at this school. But it's very, very difficult to solve analytically except in these special cases. So the name of the game is to look at limiting cases where one or two of the terms dominates over the others. That's always part of the name of the game anyway. And in particular, we can take ratios of terms in this equation to identify which terms are important at any given time. Lots of different ways to do that. I'm going to perhaps unwisely, I'm going to try to do a different share here. I'm going to try to share an iPad screen as a Blackboard. Right. So so we've got our momentum equation. We want to look at different balances that might prevail in that equation in different regimes. Again, this first few minutes is really basic stuff, and we'll get to progressively less basic things as we move on. So don't lose heart. Right. So we just take ratios of these different terms, and one thing we might look at, for example, is the ratio of the inertial term to the viscous term. So that would look like, in other words, the ratio of this u dot del u term over, in the form we've written it, u nu del squared u. And the game we're going to play is we're going to assume that there's a single length scale in the fluid, L, let's say, and a single velocity scale, a characteristic velocity scale in the fluid u. And we might eventually talk about a characteristic time, but let's come back to that in a second. And because of that, we're going to assume that derivatives, like del, are 1 over a characteristic length. So in other words, this inertial term is going to look scale like u squared over L over nu u over L squared, which is just u L over nu, which most of you will recognize as the Reynolds number. So that's one of our characteristic dimensionless numbers that will help us characterize the flow. And you play this game for other terms too. So let's think about the Ekman number. So the Ekman number is the ratio of the viscous term to the Coriolis term. So that's it's going to be nu del squared u all over. We'll keep the 2 in there, but sometimes you might throw it away. So that's nu u over L squared all over 2 omega u, which is just nu over 2 omega L squared. And again, you might lose the factor of 2. We'll call that Ek. And then the other one that we'll talk about a lot today is the Rossby number, which is just the ratio of the inertial to Coriolis forces. So inertial over Coriolis, which again is just u dot del u over 2 omega cross u, which is just going to be, let's u squared over L to omega u, which is just going to be u over 2 omega L. We'll call that RO. Okay, so these are good things. These are our characteristic numbers that kind of will help us establish what regime we're in. So we're going to talk about these a lot today, and you've seen them before probably. By the way, you can do this whole thing right at the beginning instead, in maybe a more formal way, by defining characteristic length scales and velocity scales and time scales right at the outset, and expressing your equations in non-dimensional terms. And in which case, so for example, you might write the velocity as some non-dimensional velocity times a typical u scale, or lengths times in terms of a non-dimensional length times some typical length scale. And if you did that and rewrote the Navier-Stokes equation in that way, of course you get explicitly factors of Reynolds number and Rossby number and all the rest of it popping out in the equations. That's not the approach I'm going to take today, but it's an equally valid one. It's the same results. So let's think about this stuff for a second. So the Rossby number, for example, right, which we wrote as 2 u over 2 omega L. What does that mean physically? Well, roughly speaking, it's of order 1 over the rotation, the angular velocity rate over L over u, right? So that is roughly the rotation period over a dynamical time, or convective overturning time, if you want. So in other words, this is a measure of, again, both the Rossby number and the Ekman number are telling us something about the relative strength of Coriolis forces and other terms in the Navier-Stokes equation. And if the Rossby number is small, so RO much less than 1, that's telling us that Coriolis forces are important relative to relative to inertia. So the case I like to think about it, on Earth, you might think, for example, about the contrast between flow on very large scales, which overturn very slowly. So if you have a very large length scale and a slow velocity, the overturning time is long, and Coriolis forces have a lot of time to change the trajectory of fluid parcels, to have some influence. On very small scales, they don't. So the difference here is, if you flush your toilet in the northern hemisphere, it doesn't actually spiral a different way than it does in the southern hemisphere. Because on the scale of your toilet, on the scale of, L of half a meter or something like that, lots of other stuff matters more and then the Coriolis force, right? Another equivalent way of thinking about it is that the time scale for that motion is very, very short compared with the overall rotation period of the Earth. On very large scales, things like hurricanes really do spiral one way in the northern hemisphere and one way in the southern hemisphere by and large, because they occur on large enough length scales, long enough time scales that that the Coriolis forces have time to change those trajectories. Right. So let's think for a second. Let me just make sure that I'm not skipping ahead too much here. Well, let's go ahead and ask what some of the consequences of these things might be. Well, I'll go back to the PowerPoint for a second. Okay, so we've got that in mind. We've got these different regimes in mind for rotating fluids. And the point is that if we know something about the advantage, I guess, of doing the non-dimensionalization right at the beginning is that it becomes clearer and more explicit that if you have two flows that have the same values in these non-dimensional parameters, they're going to give you the same solution. They're going to behave in the same way. That's a little bit less obvious if you do it as I've done sort of after the fact, but it's true either way. So these help us characterize the flow. And the most famous example, which I'm sure you've seen before, is just the idea that the contrast between flow at low Reynolds number and at high Reynolds number. So at low Reynolds number, this is just flow over a blunt obstacle from this album of fluid mechanics. At low Reynolds number, that is laminar flow, there's this sense of reversibility. You can follow the motion of a parcel fluid quite well forwards or backwards in time. As you go to larger and larger Reynolds numbers, the flow eventually becomes turbulent. You lose that sense of exact predictability, except in some statistical sense, and you might call the flow chaotic. And there's all sorts of consequences associated with that. So, I mean, you've seen examples of turbulent flow before, but just to give you a sense, this is a movie of the Kelvin-Helmholtz instability, two layers of fluid in relative motion. The instability isn't important for our purposes today. It's just that, it's an example of something that drives a flow, and for low enough viscosities, it's going to look turbulent. And the thing I wanted you to remember is just that very generically in a turbulent flow, there's a wide range of spatial scales and velocity scales present. The reason I mention that is because it's easy for us to think about, and it's when I tell you something like the Reynolds number of the sun or the Reynolds number of a particular flow, that is on some scale. And generically in astrophysics, those numbers tend to be really big, not because the microscopic diffusive coefficients are really, really tiny. It's just that the length scales we're talking about are typically big. There's always some scale, but there's a huge range of scales of motion present. And on some scales, those Reynolds numbers and everything can be very different. So it's useful to keep in mind. Another consequence that's worth keeping in the back of your head is just that it's a well-known result that if you pluck down a spot of dye or something in a turbulent fluid, it will disperse much more readily than it would under the action of just microphysical diffusivity. So those eddies tend to grab onto the thing and spread it out. And that motion is often described, whether well or not, in terms of a so-called eddy diffusivity. You could estimate it to order of magnitude by taking typical velocities times a typical length scale in the fluid in the turbulent flow. So you might call that this eddy diffusivity, and you could define an eddy diffusion time in the way you would define any other diffusion time, so L squared over some diffusivity. In this case, if you just plug those two expressions in together, you're going to find that the eddy diffusion time is the dynamical time. It's it's L over U where for the turbulent flow. So in other words, that if you pluck something out of a turbulent flow, it disperses on roughly the dynamical time rather than on what is typically the much longer microphysical diffusion time. And meanwhile, at low Reynolds number, I couldn't resist showing you this famous, this is from a series of movies made a long, long time ago, the 50s or 60s, I forget it, the National Committee for Fluid Mechanics films, just looking at the behavior of fluids at very low Reynolds number.
This fluid is stretched round the annulus.
So he's plopped in some dye in a very viscous fluid. That is one where the viscous term is large. And so the Reynolds number for the imposed motion is very small.
The cylinder is turned back, attracted to its starting position.
And so there's this sense of reversibility and all this. So I'll invite you to look at those yourself. So now I want to think about the peculiar effects that rotation has and the dynamical regimes that that sort of gives us in a fluid. And the particular, again, motivating question that I want us to think about for a second is just why you see, when you look at the wind patterns on Earth, you see something like this, and how that comes out of the Navier-Stokes equations. So the equations that we could write down, I mean, we just take the equations that we've written them above, but let's simplify for the moment to the case of a relatively thin atmosphere, and we'll look at just the Cartesian plane layer that's at some fixed latitude somewhere on that rotating planet. So we're in a non-inertial frame. There is a Coriolis force. We just write down the equations. And they'll look something like this. So the Coriolis term here I've written as, in terms of this Coriolis parameter f, so the top equation is going to be the x component of the momentum equation. The bottom one is the y component of the momentum equation for the y velocity v. And I'm suppressing the vertical coordinate for now. So we're just talking about the horizontal balance. So this is what the equations look like. And let's suppose now that the Rossby number and the Ekman number of the flow are both small. What that means, and then let's think also about steady solutions and ask what happens. So the only things that are left, well, in the vertical we'll have gravity, but in the horizontal directions, the balance then must be between the Coriolis term, 2 omega cross u, and the pressure gradient, del P. Or, in other words, going back to these equations between, for example, this FV and minus 1 over rho dp dx. So in equations, it just looks like this. And this situation where we have pressure gradients balancing Coriolis forces is what's called geostrophic balance. It's something that occurs very often on rotating planets or stars, because stars are often in this regime where Rossby number is fairly small, at least on some scales, and viscous forces are also important. So the Ekman number is also small. That is, Coriolis forces are important relative both to inertia and to viscosity. That Ekman being small, by the way, is a much more robust assumption than Rossby number being small. We'll come back to that in a second. Viscous forces, microphysical viscosity, are almost always negligible in stars. The Rossby number doesn't always have to be small. So there are stars that are rapidly rotating and others that aren't. Okay, so what are the consequences of that? Well, one consequence, let's see, let's try this again. Let's try the iPad once more. So one thing we can work out is just the consequences for the flow. So let's suppose that we go back to the iPad for a second. So suppose we want to understand what the flow, how the flow and the pressure gradient are related. So let's consider u dot del P, because as I said, you might have expected in the absence of rotation rate that in the absence of rotation that the flow, there would be a flow from regions of high to low pressure. And we want to see how that's affected, how that is affected by the presence of Coriolis forces. So in other words, we're going to do UVW dotted into dP dx, dP dy, dP dz. Only we're going to ignore the vertical flow. We're just looking at the horizontal balance. So if, so in other words, we want u dP dx plus v dP dy. And we're going to assume that the flow is geostrophic. So we had from above that, u is minus 1 over f rho naught dP dy, and v is, similarly. So we go back to my expressions here. So V is 1 over F rho naught dp dx. Okay, so we can, so U dot del P then is just minus 1 over F rho naught E squared P dx dy plus 1 over F rho naught E squared P dx dy, which is 0. So in other words, the flow is along the isobars. That is the lines of constant pressure. There's no flow across the lines of constant pressure. And that's in a way, an interesting result. That's why if you look at these maps, that's why when you look at these things, the flow is clockwise around these regions of high pressure and counterclockwise around low. You can figure out the sense of it, which direction it has to go by just thinking about the balance of Coriolis and pressure gradient terms. Another kind of consequence of this, which is a little bit, which comes up a lot in stellar interiors, is the related concept of thermal wind balance. So so suppose we've got a situation where we're in both geostrophic balance in the horizontal and hydrostatic balance in the vertical. And think again, for the moment, let's think again about a atmosphere or something on a rotating planet. So we've got some horizontal variation of density or temperature. So this is not a hypothetical. This happens, for example, on a planet like Earth that is differentially heated, so the equator is hotter than the pole. So you have some regions that in the horizontal direction, that is the pole to equator direction, are hot and some that are cold. And that for any sensible equation of state, the cold ones are going to be denser than the warm ones. So you've got some horizontal variation in density, in other words. Now, the cold regions of the atmosphere, the dense parts, in those regions, because dp dz is minus g rho, right, the pressure gradient is going to be steeper in regions where the density is larger. The gravity is the same also everywhere. So the pressure gradient is steeper. That means that the spacing between the isobars, the lines of constant pressure, has to go down. So in other words, if you end up with a situation like this, we're looking at it from the side, the atmosphere sort of slumps down in these regions in the regions where it's dense and cold. You can actually see this effect on Earth, for example. This is the mean height of the 500 of a particular pressure surface, the 500 millibar surface. That's on a particular time, so in January of 2003. And the point is just that the atmosphere is thicker, effectively. That particular pressure surface is higher up in the atmosphere in the regions where it's hot and less dense. So here at the equator, and it's thin, it's slumped down in those cold polar regions. What that means is that the constant pressure surfaces, just to go back to our diagram for a second, the constant pressure surfaces tilt downwards. So if I sit at one physical spot in the atmosphere, that means there is a horizontal pressure gradient, right? In other words, I look around at my level and I don't see the same pressure over there. So there's a pressure gradient at fixed horizontal levels, which will drive a flow. Fine. But we know from the stuff we just did that the flow is not just along, from regions of high pressure to low pressure. It's affected by the Coriolis force. It's geostrophically balanced. And so the net effect is that the magnitude of the east-west wind, the zonal flow, changes with height, and it's linked to those horizontal pressure gradients. Now, rather than go too much into, I'm just going to put up the equations. This is one of those things where I think it's actually easier to understand in equations than it is in some ways in pictures. If you just take your geostrophic balance equations that we had a second ago, add in the vertical equation for hydrostatic balance, and manipulate them basically essentially by just taking the curl. So d by dz of one equation, d by dx of another. You can combine those to get equations that look like these on the bottom. So in other words, the vertical shear in the wind, so dv dz, for example, is related to minus g over f rho naught d rho dx. So you have some horizontal density gradient, and that's linked to the vertical shear in the wind. And similarly for the other horizontal flow. If you're looking, if you're a student and you're looking to test yourself a bit, you can try to do this for spherical geometry. This is nicked directly from an exam question that I gave students last year, so have fun. It's so basically, you take the momentum equation in a rotating spherical body, you can write the rotation vector in a particular way. So here I've adopted coordinates where theta is co-latitude and phi is longitude. And I've written it in a slightly different way than I did before because I'm incorporating the effects of centrifugal forces in a particular way. Anyway, basically you want to just take the phi component of the curl of the momentum equation, assuming that Ekman number is small and Rossby number is small. And here I'm also allowing for a base state plus small perturbations around that state. And if you want to write that as I've done here, so you crank through it and you'll get an equation that looks like this one at the bottom. That the omega dz, that is the gradients of z along the rotation axis. So z is aligned with the rotation axis here, are linked to horizontal variations, latitudinal variations in the entropy. If you want to write it in that way, you'll need to use the fact that entropy gradients, you need to have a link between the entropy gradients and pressure and density gradients. So it looks something like the thing on the bottom right here. Okay, so what does this mean? This is kind of why I've prattled on about geostrophic balance and thermal wind balance for a second. The point here is that if there were no horizontal density variations, no horizontal entropy variations, then d omega dz would be 0. And that's what's known as the Taylor-Proudman theorem, or a version of what's known as the Taylor-Proudman theorem, which would say that the flow really likes to be constant along lines parallel to the rotation axis. And there's lots of manifestations of that, lots of interesting consequences of it in geophysical fluid dynamics, but also in stellar physics. And it leads to some interesting puzzles. So for example, if we look at a helioseismic map of the sun's internal differential rotation, we'll hear lots more about this later in the week. This one is from Rachel Howell's Living Review. You see that the sun's, so the contours are giving the isorotation contours. So red is fast here and blue is slow. The sun has a differential rotation, fast equator, slow pole, that largely imprints to the convection zone, and then a transition to nearly solid body rotation below the base of that zone. But the isorotation contours are not particularly cylindrical. They're closer to radial lines, and there's been a lot of discussion about why that is. One possibility is that there are these baroquinic terms. So another way of writing this ds d theta term is in terms of a baroquinic term, del p cross del rho. So there's got to be some baroquinicity. So one way to tilt the isorotation contours away from the cylindrical. Alternatively, the Rossby number of the sun might, we've assumed that the Rossby number is small and Ekman number is small. The rest of it, maybe interesting to know that the Rossby number of the sun is also a subject of some debate right now, because it's got a typical convective velocity in it. And the question is what, if you want to estimate the Rossby number of the sun, you need to know what that velocity is. And right now there's a bit of a controversy about this, but there are some indications that the amplitude of deep-seated velocity motions in the sun is quite a bit lower than simulations or simple mixing length style arguments would predict. And maybe we'll come back to this later. But the point is that the sun, that would actually tend to make the sun a much lower Rossby number thing than we currently think, which would help with it in other ways. This is an inference from Hanasogi et al. 2012 based on helioseismic inference of the large-scale velocity amplitudes. Anyway, now, so that was all hydrodynamic stuff. I want to think now about some stuff to do with magnetic fields. And so we'll go back to the idea of, we're going to talk now about the induction equation and some of its consequences. Now, before we go back to equations, I wanted just to try to fix in your mind a physical picture that we're going to use for stuff. So the picture I want you to imagine is that in the limit where you have a fluid that is plasma that is highly ionized, it's a very good conductor. Magnetic fields behave, I'm going to state without proof, basically, that magnetic fields behave very much as if they were a set of elastic strings that move with that fluid. And to kind of flesh out the analogy, we need to imagine that those strings are infinitely long, so those represent the field lines. We can have bundles of field such that the density of the strings, that is the number per area threading some locally perpendicular thing, is proportional to the strength of the field. The orientation of the strings is going to define the orientation of the field. They can form loops, but they can't end in order to give del dot b equals 0, that sort of thing. And again, the point is that they're carried along with fluid as if they were frozen into the fluid. That's the limit that we're going to talk about essentially today. They're unchanged by motions along the fluid, the field line. And if, with that kind of physical picture in mind, if you want to put it in equations, we're going to assume that the energy density in the magnetic field is proportional to b squared over 8 pi. And we have some tension, as if we have some collection of magnetic field lines that forms a bundle of some radius a. The tension of that flux bundle is of order a b squared over 4 pi. That's the kind of thing we want to have in the back of our heads. So let's go back to the blackboard for a second. There we go. Okay. So again, the equation that we're going to be talking about is the induction equation, which looks like this: del d del cross b, and we'll write it in a form where the diffusivity is constant as a function of position. So it just looks like this. So there's an induction piece and a diffusive piece. And again, we can take ratios of these terms to get some sense of what is happening. So if we take the ratio of these two things, del cross b over eta del squared b, play the same game as before of assuming some characteristic length scale. That's going to look like eta b over del squared. It's going to be, and this is so, you know, this is called the magnetic Reynolds number. Oh, sorry. Sorry. So this is the magnetic Reynolds number. Which is another one of our characteristic things that we're going to talk about a lot. And the limits here to think about, so eta, right, is the magnetic diffusivity, which has, in CGS unit, it's c squared over 4 pi sigma. Sigma is the conductivity. And so the limits here are that as Rm goes to infinity, that's sort of the high conductivity limit. As Rm going to 0 is the lousy conductor limit. So that, in other words, as Rm goes to 0, in other words, as the diffusion term gets big relative to induction, induction gets small, we just have a diffusion equation. dB dt is eta del squared b. So that is the diffusion equation, right? And so the field just decays away on some characteristic time, which we can figure out, which is, you know, eta b over L squared. So that's so that's called the ohmic diffusion time, or the magnetic diffusion time. Okay, so this is all basic stuff, but let's think for a second about what kind of values are we talking about in astrophysics? So let me just grab a couple things here. So let's suppose that we're thinking about an area of the sun fairly deep down. So somewhere deep in the convection zone, we might have something like eta of order 10 to the 2 centimeters squared per second. And so on a scale, on a sort of macroscopic scale, like the size of the convection zone, we might have something like 2 times 10 to the 10 centimeters. And so the magnetic diffusion time on something like that scale, L squared over eta, is going to be, you know, big, 4 times 10 to the 20 divided by 10 to the 2. So, you know, some order 10 to the 18 seconds, or, you know, a few times 10 to the 10 years. So in other words, stars, if I hadn't lied to you about this value of the magnetic diffusivity, stars are pretty good conductors. And so one consequence of that is that even that fields can persist for a really long time. So for example, when we look at higher mass stars, so where there's no surface convection and we just have a large scale magnetic field that doesn't seem to be linked to surface convection, it's plausible that those are relics of the star formation process, or, you know, some other process early on in the star's life, because the decay time for these stars is, the decay time for a field is really, really long, billions of years. So a thing can persist unless you tear it up by small scale turbulence or something like that. The field can persist for a really, really long time. Maybe a useful number to keep in the back of your head is just that if you looked at the magnetic Reynolds number for a person-sized thing, So, U of 1 meter, 1 meter moving at, 1 meter per second, L of 1 meter. In a plasma at about 10 to the 6 Kelvin, Rm is about 1. So if you look at the sun, if you were marching around in the sun at a region where the temperature is about 1 million Kelvin, a person-sized thing would have an Rm of 1. So when we say that the Reynolds number, the magnetic Reynolds number of the sun is really, really big, I mean it is, but it's big because not especially because the diffusivities are so small. It's mostly just that we're talking about really, really big length scales. Right. So how much time do we have? Not much. Okay. I want to think for a second about just some of the intuition you can get by thinking about these things as field lines. So in the last 6 or 7 minutes, I want to just think for a second about this picture of magnetic fields as a collection of elastic field lines that do various things when you stretch them or whatever. And the analogy that you might think about is, I mean, look, if I took a string and I plucked it a little bit, I put a mass on a string, and this is at minus L and plus L. I could write down a differential equation for the displacement of the string as a function of time. Right? I could just F equals NA, right? So magnetic fields behave a little bit like that. They have some tension associated with motions transverse to the field. So if I have a collection of magnetic field lines, like so, forming some bundle, if I try to bend the fields, they will resist that bending. They'll resist that bending, and some signal will propagate down at a characteristic speed. And the characteristic speed at which signals propagate by magnetic tension is called the Alfvén velocity, b over, in these units, square root of 4 pi rho. Okay. In numerical terms, just again, because we're going to use it here in a second, for a plasma, so I'm going to write this down, 2 times 10 to the 11, b over n to the 1/2. So this is for a plasma that's 90% hydrogen, the rest 10% helium, and this is number density in particles per centimeter cubed. This is in Gauss, and the whole thing is in centimeters per second. Okay, so we'll use that in a second. The other thing you can do is try to squeeze the field lines together. So if I took this whole bundle and I don't bend the field lines at all, I just kind of compress them, they'll resist that too. And we call that resistance. So things that don't bend the field lines, but you try to change the spacing between them, they resist the resistance we might call the magnetic pressure, b squared over 8 pi. Okay, and the reason these things are useful is because if we're able to calculate the magnetic pressure or the magnetic tension, we can sometimes very quickly figure out whether magnetic fields are likely to be important or not in a given problem. By the way, this is not, I'm not just making this stuff up. I mean, mathematically, what these things are all coming from is the Lorentz force term, right? So we could write that in terms of b dot del b over 4 pi minus del b squared over 8 pi. So this is the tension. This is the pressure term. You have to be a little bit careful because if you're this analogy is not perfect, but this mathematical decomposition is. The only thing you have to watch out for a little bit is just that split in this way, you can have components that that exactly cancel from these two terms that you don't necessarily need to calculate. Okay, so in the last few minutes, I wanted to just give you a couple of examples of how you'd use this stuff. So let's imagine that we're thinking about the sun, and we want to think about, that's my timer. Okay. We want to think about whether or not magnetic fields are likely to be important in a particular problem, which is, we've got a coronal loop sticking out of the sun, some magnetic field line that's threading the solar surface, and it's being dragged around by convection down here. And it's got some characteristic length. Let's say it's 10 to the 9 centimeters. And it's got some characteristic number density, which is say 10 to the 9 centimeters cubed. and it's got B of maybe 100 Gauss, just to pick a number. And let's say that the convection is dragging it around on some time scale, which is of order 10 minutes. So the question is, does that convective dragging lead to waves that propagate down this loop or not? And the question we really want to ask then is, what is the time scale for magnetic signals to propagate down the loop compared to the time scale on which you're dragging this thing around? So let's just do it. So the Alfvén velocity from our formula up there, so this was just 2 times 10 to the 11 B over n squared 1/2. So that's going to be 2 times 10 to the 11 10 to the 2 over 10 to the 4.5. This is all in centimeters per second. So I pre-computed this. Yeah, right. So this is around, this turns out to be, for perspective, about 6,700 kilometers per second. And so the time scale for it to propagate down the whole loop is, on the order of a second. So in other words, these signals move very quickly, driven by magnetic tension. And that, because of that, we don't expect wave-like behavior, right? In other words, the loop can just adjust quickly enough to this convective dragging around that you wouldn't get that. Now, if you had something like a flare with a time scale of, 0.1 seconds or something like that, you might expect that there's some wave that gets set up in the coronal loop instead. So just having this kind of characteristic view of time scales or length scales can tell you one or two things. Let me do one more example before we quit, and that is just the idea of accretion. So you could also do this for magnetospheres, the Earth's magnetosphere in response to the solar wind. So let's suppose we've got some object here, and we've got it's got a dipole magnetic field, and it's in a spherical accretion flow. So its material is infalling at some rate, and it's got a certain velocity and so forth. So again, the magnetic pressure of the thing we're going to assume is b squared over 8 pi. And if it's a dipolar field, then it's going to look something like BR is going to be a constant times over r cubed. It's 2m cos theta, and b theta similarly. So in other words, the magnetic pressure then is going to be some constant, m squared over 4 pi times 1 over r to the 6th. The important point is that scales like 1 over r to the 6th, so don't worry too much about the constants. And the thing we want to do is ask, we might expect before we do any calculations, if you have some spherical infalling wind, you expect that it's going to compress the magnetosphere, and that the extent of the compression and thus the extent of the magnetosphere will depend on the relative strength of those two things, on the magnetic pressure versus the pressure, the dynamical pressure of the infalling wind. Really, what we're doing is another example of just dynamical balances in the Navier-Stokes equation. We're equating the inertial term of the wind, if you like, to the magnetic, to the Lorentz force. But let's do it in this way. So the wind pressure, if you like, is going to be of order rho wind times v wind squared. So we need to figure out what those two things are. And if it's just free fall, then we're going to say that the velocity of the wind is just going to be, if this thing has mass m and your distance r away, it's going to be 2 gm over r to the 1/2. And the density, let's say the mass accretion rate, which we usually can measure, right, is something like m dot. So the density of the wind is going to be, if it's spherically symmetric, just m dot over 4 pi r squared v wind. So just by looking at these two things, so looking at the form of the magnetic pressure here, so we've got magnetic pressure doing this thing, and we've got gas pressure doing this thing. It seems pretty clear that at small enough radii, the magnetic pressure has to dominate, right? It's scaling very differently with radius. So there's going to be some radius at which, the magnetism wins, and some radius at which the dynamical pressure of the infalling wind wins. And you can equate those two. So the point at which so P mag equals P wind at some particular radius, which we'll call the magnetospheric radius, which turns out to be, if you do this, it ends up being, mass of the star squared over m dot times 2gm to the 1/2 all over to the 2/7 or something like that, which would allow us to estimate the size of the magnetosphere of the star. So if, for example, we were looking at a neutron star with, say, r of 10 kilometers, m of a solar mass, and b of 10 to the 9 Gauss, accreting at about 1/10 of the Eddington rate. So that's so m dot is about 10 to the -9 solar masses per year. That would tell you that the magnetospheric radius is about 10 r star. Which isn't too bad, actually. And you could do a similar thing for estimating the size of Earth's magnetosphere in response to the solar wind, which likewise is not too bad an estimate. The reason that I'm telling you these things is because in astrophysics, look, very often an order of magnitude answer is as useful to us, at least in the short term, as a more detailed answer. If what you want to know is, are magnetic fields important in this problem? Are they dynamically strong enough? Are they do they have the right time scales and so forth? Then this kind of thing is usually enough. Right, I think I'm out of time, so I'm going to stop there and go back to the PowerPoint just for the last second here. So we've gone through a couple of examples of this stuff, and if we'd had time, we could go through a little bit more, but you can do this on your own. Again, the reason that I prattled on about this stuff for a minute is just that, look, when we go to these complicated nonlinear states, we can't generally solve for the motion in great detail, but knowing what dynamical balances are there can tell you a lot about the flow. And the analogy I like to think of is, look, if you had these two bunches of guys playing tug of war, and let's say one of them is called Coriolis, and the other one's called pressure gradients, and you add, little old me onto one side of it, it ain't going to make a difference, right? The predominant balance is between these guys, even if there's lots of other effects present. Now, the caveat to that is that sometimes the interesting dynamics, the dynamics you care about, only occur at that second order. So even if the dominant balance is geostrophic, you might be interested in the dynamics, the ageostrophic dynamics, which occur, only because, little old me comes onto one side or something like that. The other reason I mentioned this is because in the next lecture, when we look a bit at some of the nonlinear results on convection and dynamo theory, it's useful to keep in mind that the dynamical balances that prevail in a real star can sometimes be very different from the ones that you see or are able to achieve in a simulation. And the basic punchlines from today are really just that these equations are simple in concept, but they're difficult to solve. And so we look for limiting cases where one term dominates over the other. Examples we've talked about today are geostrophic balance and thermal wind balance in particular, and in the MHD case, this frozen flux limit where the things behave more or less as elastic field lines. I'll stop there. Thanks for your time.